friends, in wave optics up to this we discussed at least the 10 MCQ asked in All India PMT and also Neet exam. Today we are considering the more MCQ that is asked in 1996 All India PMT. In a Fresnel by prism experiment, the two position of lens gives the separation between the slit as 16 cm and 9 cm respectively. What is the actual distance of separation? Now listen, in wave optics we discuss about the Fraunhofer diffraction, not Fresnel diffraction. But when we discuss about the theory, at that time we discuss also what is the difference between the Fresnel and Fraunhofer. In Fraunhofer diffraction, the lens generally is used to focus the parallel beam on a slit, and also after the reflection, what is the parallel beam is reflected, that is focused on a screen with help of a convex lens in Fraunhofer diffraction. While in Fresnel biprism or the Fresnel diffraction, here generally the lens is not used, but here in biprism the two position of lens gives the separation between the slit as you keep the lens at two different positions from the slit. One is 16 cm, second is 9 cm. So what is the actual separation between the slit? So actual separation between the slit is under root of I1, I2. I1 is given 16, I2 is given 9 cm. So here the distance of the slit from the lens is I1 is equal to 16 cm and I2 is equal to 9 cm. Right? Actual distance of separation D is equal to under root of I1, I2 is equal to under root of 16 into 9. So is equal to 4 into 3. That means the 12 centimeter is our answer. Where is it? With help of the lens we find out the distance separation at 16 centimeter and at 9 centimeter are different. So what is the real separation between the slit? Okay. After that, next, color appears on a thin soft film and on a soft bubble due to phenomena of. We have the experience as the sunlight is incident on a layer of soap solution of the soap liquid or the bubble of a soap. At that time, we feel that the colorful bubble or the colorful layer is shown. So here, which phenomena of light is responsible for this color appears on thin soap film or soap bubble? So here, interference phenomena is responsible to appear the colorful appearance of the thin soap layer or the soap bubble. So interference is the answer, not the dispersal of light. Dispersal of light is phenomena when the chromatic light is passing through the prism. Due to the reflection phenomena, as the light is emerged out from the prism, at that time it divided into its constituent color. That is the dispersion phenomena. But here, the interference phenomena is the place or the responsible for color appears on a thin soap film or the soap bubble. Clear this? Okay. After that, the next is the distance between the 2 points on a paper is they are observed so that the view line of observer is perpendicular to them. The diameter of an eye of an observer is 2 millimeter. Diameter of an eye is 2 millimeter. Therefore, the resolution of eye, here the D is given, D is 2 millimeter. Diameter of eye. Small d is 2 millimeter. For which minimum value of d, both points will be observed. Right? So here the resolution of phi theta is equal to lambda upon small d. That is the equation 1. Now, if the distance between the 2 points is x and the distance from the I is d, if distance between 2 points is x and from I is capital D, then theta is equal to x by capital D. X by capital D. From these two equations, here x capital D is equal to lambda upon D. Therefore, x is equal to lambda D upon D. Here the wavelength are not given. Now listen. Capital D not given. Consider lambda is equal to 5000 angstrom. Capital D is equal to 50 meter. So in that case, we substitute the value. So pi into 10 is 2 minus 7 into 50 upon D. 2 into 10 is 2 minus 3. We get the answer is 12.5 centimeter. 12.5 centimeter. Now keep in mind that here the wavelength and diameter or the distance of these 2 points from the eye is not given. This D. And wavelength of the light used is not given. So here consider this value to obtain the value. Answer is 12.5 centimeter. Again, the resolution of I theta is equal to lambda upon small d. D is the diameter of I. Lambda is the wavelength used. If the distance between the 2 points is x and the distance from the I is capital D. So theta is equal to resolution, theta is equal to x by d. Comparing equation 1 and 2, we obtain x upon capital D is equal to lambda upon small d. Therefore, we require the x because what is the minimum value of the both points will be observed. So x is equal to lambda d upon capital D. Consider the value of lambda and d is 5000 angstrom and capital D is 50 meter. So we obtain the 12.5 centimeter is the answer. Okay. Now next, in Young's double slit experiment, if the width of the slit is made 1/3 times width of the fence becomes the n times, then n is equal to 1. What it says that in Young's double slit experiment, if the width of the slit initially that is the d, now we decrease this width by 1/3. So in that case, what should be the fringes becomes width of the fringes. Width of the fringes beta is equal to lambda d upon d. Lambda d upon capital D. Therefore, beta proportional to 1 upon d. Small d is the width of a slit. Right? Therefore, beta 1 proportional to 1 upon d1 and beta 2 proportional to 1 upon d2. Therefore, beta 2 upon beta 1, beta 2 upon beta 1 is equal to d1 upon d2. d1 upon d2 is equal to d upon d by 3 is equal to 3. Now here given the width of the fringes becomes the n time. Therefore, beta 2 is equal to n beta 1 upon beta 1 is equal to 3. Therefore, n is equal to 3. N is equal to, that is our answer. Now here, we have to use the equation of the width of a fence. Beta is equal to lambda capital D upon small d. Therefore, capital D is the distance of the screen from the slit, lambda is the wavelength of light used, and small d is the width of a slit. Therefore, width of a fence is inversely proportional to the width of a slit. For beta 1 proportional to 1 upon d1, beta 2 proportional to 1 upon d2. Taking the ratio of these two equations, beta 2 upon beta 1 is equal to d1 upon d2. Now we decrease the width of a slit by 1/3. Therefore, d2 is d by 3, d1 is original width of a slit, therefore 3. At that time, the range of the width becomes the n times. Therefore, beta 2 is n times of d1 upon b1. b1 cancel. Therefore, n is equal to 3. Clear this? Okay. Now, next is, if waves of light having intensity I1 and I2 passes through any region in the same time, in the same direction. So what will be the sum of maximum and minimum intensities? Now we know that the resultant intensity I is equal to I1 plus I2 plus 2 under root of I1 I2 cos phi. There is our standard equation of resultant intensity due to superpositioning of the two waves having the intensity I1 and I2. Okay. Now, for maximum intensity, take the cos phi is equal to plus 1. Therefore, I max is equal to I1 plus I2 plus 2 under root of I1 I2. Because the cos phi is equal to 1. Okay. And for minimum intensity, consider cos phi is equal to minus 1. Therefore, I minimum becomes I1 plus I2 minus 2 under root of I1 I2. We require the sum of minimum and maximum intensity. Therefore, I maximum plus I minimum is equal to addition of these two, I1 plus I2 plus 2 under root of I1 I2 plus I1 plus I2 minus 2 under root of I1 I2, that is cancelled. Therefore, twice time of I1 plus I2 is the addition of I maximum plus I minimum. That is the answer. Again, here we are using the equation of the resultant intensity due to the superpositioning of the two waves having the intensity I1 and I2. So equation I is equal to I1 plus I2 plus 2 under root of I1 I2 into cos phi. Phi is the phase. Okay. Now for the maximum intensity, consider the cos phi is equal to 1. That means the phi is 0. Therefore, I maximum is equal to I1 plus I2 plus 2 under root of I1 I2. Now for minimum intensity, the phase phi is equal to pi, cos pi is equal to minus 1. Therefore, I minimum is equal to I1 plus I2 minus 2 under root of I1 I2. Take the sum of these two. So this plus this minus is cancelled. So I1 2 times, I2 also 2 times. Therefore 2 is common, I1 plus I2. Okay, now next numerical that is asked in 2013. In Young's double slit experiment, the slits are 2 mm apart and are illuminated by the photons of the two wavelengths. Lambda 1 is equal to 12,000 angstrom and lambda 2 is equal to 10,000 angstrom. At what minimum distance for the common central band points on the screen? Screen is 2 meters away from the slit. Will a band fringes from one interference pattern coincide with a band fringes from the other? That means at what minimum distance, due to the lambda 1 wavelength, the one band fringes, and due to the lambda 2 wavelength, the first or the next band fringes are superposed at minimum distance. We have to find out this. So here the lambda 1 and lambda 2 is given. Here we assume that suppose N1 band fringes for lambda 1 and N2 band fringes for lambda 2 are superposed. Superposed on each other. Therefore, we can write N1 lambda 1 is equal to N2 lambda 2. Therefore, N1 upon N2 is equal to lambda 2 upon lambda 1. Lambda 2, 12,000 upon lambda 1, 10,000. So it's equal to 5 by 6. Therefore, we can obtain N1 is equal to 5th band fringes and N2 is equal to 6th band fringes are superposed at x distance from the central interference pattern. Suppose what superpose at x distance from center. Therefore, x is equal to N1 lambda 1 capital D upon small d. N1 is 5th order, lambda 1 12,000 and capital D is 2 meter already given, and width of the slit is given the 2 millimeter. So 2 into 10 is 2 minus 3. 2 into 10 is 2 minus 3. Therefore, here there is the 12,000, that means the 10 is 2 minus 10 meter. Therefore, 6 into 10 is 2 minus 3 meter, that means the 6 millimeter. At 6 millimeter distance from the central fringes, the 5th order band fringes due to wavelength lambda 1 is equal to 12,000 and 6th band fringes of the wavelength lambda 2 are supposed at distance x is equal to 6 millimeter from the central direction. So same type of the numerical we discussed in exercise. I think the 10.6 or 10.7, and that is asked in this year board exam. Again, in Young's double slit experiment, the slits are 2 millimeter apart and are illuminated by the photons of the two wavelengths. Lambda 1 is equal to 12,000 angstrom, lambda 2 is equal to 10,000 angstrom. At what minimum distance from the common central band fringes on the screen, 2 meters away from the slit? Will a band fringe from one interference pattern coincide with a band fringe from the other? For that purpose, we assume that suppose N1 band fringe for lambda 1 and N2 band fringes for wavelength lambda 2 are superposed on each other. Therefore, N1 lambda 1 is equal to N2 lambda 2. Therefore, N1 upon N2 is equal to lambda 2 upon lambda 1. Therefore, 12,000 upon 10,000 is equal to 5 by 6. Therefore, n1 is equal to 5, n2 is equal to 6. Suppose at x distance from the central fringe. So at x distance, the n1 lambda 1 d upon d or n2 lambda 2 d upon small d. So is equal to, when substitute the value, we obtain the 6 millimeter. So at 6 millimeter distance, the fifth order bad fringes due to the wavelength lambda 1 and sixth order bad fringes due to the wavelength lambda 2 are superposed. Now next, a beam of light of wavelength lambda is equal to 600 nanometer. So lambda is equal to 600 nanometer, 10 is to minus 9 meter. From a distant source, falls on a single slit 1 millimeter wide. D is given the 1 millimeter, that means the 10 is to minus 3 meter. And the resulting diffraction pattern is observed on a scale 2 meter away, capital D is equal to 2 meter. The distance between the first diode fringes on either side of the central diode fringe is. We have to find out there is the central diode fringe. The first order minimum is obtained here. We require this distance. This distance is x, so we require the 2x. We require the 2x. Now, condition for first minimum. Condition for first minimum is d sin theta 1 is equal to lambda. But sin theta 1 is equal to x upon d. X upon d. Comparing these two equations, therefore lambda upon d is equal to x upon capital D. X1, we take the x1. Therefore x1 is equal to lambda capital D upon small d. Therefore, that is the distance of the first minimum from the central maximum. Therefore, the distance between two minima on either side of central maxima, distance between the two minima on either side of central band fringe is 2x1 is equal to lambda d upon d. 2 lambda 600 into 10 is to minus 9 capital D. 2 meter upon 10 is to minus 3. So it's equal to 2.4 millimeter. 2.4 millimeter. Again, here the wavelength is given. A beam of light of wavelength lambda is equal to 600 nanometer from a distant source falls on a single slit of width is given 1 millimeter. Right? The resulting diffraction pattern is formed or observed on a scale 2 meter away. The distance between the first diode fringes either side of a central band, that is the central band. So there is the first minima, first diode. There is also first diode. First diode is obtained at x distance from the central maximum or the central band. Therefore, the distance between the two first diode on either side of the central maximum. So, condition for first minima is d sin theta 1 is equal to lambda, but sin theta 1 is equal to x1 upon capital D. Comparing these two equations, lambda d is equal to x1 upon capital D. Therefore, x1 is equal to lambda capital D upon small d. Distance between the two minima on either side of central band fringe is 2x is equal to 2 lambda capital D upon small d. At this substitute the value we obtained the 2.4 millimeter. Clear this? Okay. Now after that, in the Young's double slit experiment, the intensity of the light at a point on the screen where the path difference is lambda is key. Intensity is given, that is the key. K being the wavelength of light velocity. Now, the intensity at a point where the path difference is lambda by 4 will be, what is the intensity? So we know that the equation of intensity of a light I is equal to I0 cos square here K I1 minus I2 upon U. K is the wave vector, K is equal to 2 pi upon lambda. Here the path difference is given I1 minus I2 is equal to lambda and K is equal to 2 pi upon lambda. Now intensity where the path difference is lambda, at that time I is equal to I0 cos square K 2 pi upon lambda. Here lambda by 2, that means only I0 cos square pi. I0 cos square pi. Now cos square pi is equal to minus 1 square is equal to 1. Therefore there is the I0 only. But that is given as the key. That is given as key. Equation 1. Now the point it hits. Now at a point where path difference is lambda by 4. Is lambda by 4. Therefore I is equal to I0 cos square K I1 minus I2 upon 2. Here I1 minus I2 is equal to lambda by 4 and K is equal to 2 pi upon lambda. 2 pi upon lambda. Substitute here, therefore I0 cos square. Now K 2 pi upon lambda. Here lambda by 4 into 2. Lambda cancel. Therefore cos square pi by 2. I0 cos square pi by 2. Cos square pi by 4. Sorry. Pi by 2. But we know that cos square pi by 4 is equal to 1 upon root 2 whole square is equal to 1 by 2. Therefore I0 and cos square pi by 4 1 by 2 is equal to 1. But I0 is equal to K, therefore K by 2. So here we are using the equation of the intensity of a light. I is equal to I0 cos square K I1 minus I2 by 2. Already we discussed this equation of the intensity in interference. Okay. I is equal to I0 cos square K I1 minus I2 upon 2. Here K is the wave vector 2 pi upon lambda and point at which the path difference is given the lambda. Path difference is lambda. At that point the intensity is K. Therefore here we substitute I1 minus I2 as lambda and K is equal to 2 pi upon lambda. Lambda cancel, 2 cancel, cos square pi. Cos square pi is equal to minus 1 square, that means the 1. Therefore I is equal to I0, but I is given as K. Okay. Now the point at which the path difference is lambda by 4, we substitute in this equation. I is equal to I0 cos square K I1 minus I2 by 2. I1 minus I2 is given lambda by 4 and K is equal to 2 pi upon lambda. Therefore I0 cos square 2 pi upon lambda into lambda upon 4 into 2. So 2 lambda by 2 cancel, pi by 4 is remaining. Cos square pi by 4 is equal to 1 upon 2 square, that means the 1 by 2. Therefore, I is equal to I0, 1 by 2. But I0 is equal to key. Therefore, intensity is key.